listen to my talk. So today I'm going to talk about forbidden subgraphs for bounded star-chromatic number. And I just hope that everybody here is familiar with graph coloring. And this star-chromatic number or star coloring is just a variation of purple coloring, and I'm going to explain what it is. Let me start with some nice theorem. I don't know whose theorem it is, but okay. So this theorem states that for every forest f, there exists some constant such that every f-free graph has chromatic number n most c. Okay, here f-free means that a graph does not contain f as a subgraph. So here in this talk, every containment relation is a subgraph, not induced subgraph. Okay, and this theorem states that so if you forbid some forest f, then you will have bounded chromatic number. Okay, so this theorem deals with some forbidden subgraph for bounded chromatic number. Okay. And and this work is going to work with Yu Choi from 한국외대 and Brian Park from Aju University. Okay, and this theorem motivated us. So we wanted to develop such a theorem for other colorings. So there are a lot of variations of purple coloring. For example, two distance coloring, star coloring, and acyclic coloring. So all these colorings are just a proper coloring, say vertex coloring, plus some additional condition. Okay, and our work aims to just develop such a theorem for these colorings. Okay, and in this talk, I'm gonna mainly focus on star coloring. Okay, let me define star coloring first. So star coloring of a graph G is just a proper coloring of G such that now we are going to look at the union of two colors, and in star coloring the union of two colors induce a star forest. Here, star forest is a forest of which every component is a star. Okay, star is just tree like this. Okay, it has one center and many leaves. That is called star. And star coloring, the union of every pair of two colors induce a star forest. So, and a graph is star forest if it doesn't contain P4. P4 is a path with 4 vertices. So a graph is a star forest if it doesn't contain P4 as a subgraph. So equivalently, this definition is equivalent to there is no bicolored P4. Okay, P4 is just path with 4 vertices. Okay, so star coloring of G is a proper coloring with no bicolored P4.
What about triangles?
Triangle. Yeah. What is there any problem?
Yeah, K3 doesn't contain P4, and
No.
yet it's not a star.
It must be proper coloring. So you have triangle, then each have different colors, and the union of the colors just induce just one edge. Okay, because star phrase has this shape, right? And it doesn't contain P4. And the star chromatic number we denote by KAIST is the minimum number of colors needed for a star coloring of G. And let me show you some examples. Okay. So star coloring is quite different from proper coloring. So the chromatic number of P4 is equal to 2, but the star chromatic number of P4 must be 3. So you cannot star color P4 with two colors. Okay, so if you have just two colors, then you can color like A, B, A, B, then it induces P4. Bicolored P4. And the cycle of even length. The chromatic number of cycle of even length is equal to 2. However, its star chromatic number is equal to 3. So they are different. And if you consider just some forest, so say F is forest, then the chromatic number of F is n is to 2, n moves to 2. However, the star chromatic number of F can be larger than 2, but its upper bound is 3. Okay. It's not. Is it clear? So you have forest, and can you color it with? Can you star color it with just 3 colors? Yes. But
Third vertex or something? Do you color every third vertex?
Yes, that's right. So So you have a tree like that. Then just color this 1, 2, 3, 1, 2, 3, and so on. Then, it gives us star coloring. Okay, and let's think about some trivial upper bound. So for proper coloring, you have trivial upper bound, say delta G plus 1. Okay, the maximum degree of G plus 1. But for star coloring, it doesn't work. So if you consider C5, C5, then its maximum degree is 2, but its star-chromatic number is 4. So let's look at this. So suppose it is 3 star colorable. Yeah, 3 star colorable. Then, okay, now you have a 3 star coloring of the C5. Then there must be 3 consecutive vertices with different colors, right? And now in this vertex, you can use either B or C. If you use B, then this vertex must be A. Then these 4 vertices induce bicolored P4. So it must be C. Now look at this vertex. Now you can use A or B for this vertex. But if you choose A, then AC, AC induce bicolored C4. If you use B, then BC, BC induce bicolored P4. So you cannot star color C5 with 3 colors. So this is just a counterexample of this inequality. But there is very nice upper bound in terms of the maximum degree. So in general, the star-chromatic number of G is m most delta G squared plus 1. Okay, and this is because actually you can, if you have this number of colors, then you can color vertices greedily. So suppose you already colored these vertices, and you want to color this new vertex, and look at its neighbors and its second neighbors. Okay. There are total, so the number of neighbors of V and the number of second neighbors of V is m most delta G squared, right? So because you have this number of colors, you always have one additional color which is not used on its neighbor and its second neighbor, so you can color it greedily. Then okay, so indeed if you have this number of colors, then you can color. There exists a coloring, purple coloring, say phi of G, such that for every pair of vertices U and V, with the distance most to 2 they have different colors. Okay, and this implies that there is no bicolored P4. Okay, so you have this trivial upper bound. Okay, so star coloring and star chromatic number first introduced by I don't know how pronounce it. Grunbaum. Okay, in 1973, and there are a lot of research on this topic. And recently, there are research about relation about minimum, maximum, average degree and bounded star chromatic number. So in Bu et al. In 2009, they showed that if maximum average degree is small, so 26, 11, then this implies that the star chromatic number is small. And if maximum average degree is less than 18/7 and girth is big, then star-chromatic number is almost 5. And so if maximum average degree is 8/3 and girth is at least 6, then star-chromatic number is almost 6. And there is another result, about maximum degree. If maximum degree is small enough, so it's subcubic graph. For subcubic graph, it has star-chromatic number at most 4. It is 6. It is a result by Chen al. In 2013. And there are more and more results about star-chromatic number. But most of them just deal with some small maximum average degree and bounded star-chromatic number. Okay, small maximum degree and bounded star-chromatic number. But we, yeah.
Out of curiosity, how sharp are those?
Which one?
Like any. Because I mean, like the first statement says your average degree is really close to 2.
I don't know. Yeah, I don't know. But for this result, I think it's a tight result. Yes, but I don't know what those results. Yeah. Yeah, I haven't read that paper, but I guess that they use some discharging method. And I don't know if they found some counterexample or some examples that showing that these are tight, but yeah, I don't know. So there are a lot of results like that, but we were interested in some forbidden characterization, which guarantee bounded star-chromatic number, like that, like the first theorem. Okay, so we raised this question: for which graph f does every graph have bounded star-chromatic number? Yeah, it means that just for which graph f does there exist C such that every graph have star-chromatic number at most C. Okay. And for example, every path satisfies this condition. So and let me briefly show the proof. It's quite easy. So let G be a P-n free graph. And take a DFS, so let T be a tree. So that's first search tree of G. Say this one is T. And let this vertex be root, say R. So because T is a DFS tree, So T has a very nice some property. So for every edge of G, one end of E is an ancestor of the other in T. Right? That is the definition of DFS. So this part is independent, this part is independent, and there is no edge between like these two vertices. No. But you can have edge like this. Okay? Because this is an ancestor of that, this is an ancestor of this guy. Okay? So those are only possible edges. Now just color vertices is level. The distance from R. Let phi of V be the level. So distance from R to V. So we color this vertex 0, 1, 2, 3, and so on. And because G is Pn free, so the diameter is less than n, right? Right? Okay. And the set of vertices in the same level is independent. So clearly, phi is a proper and coloring of G. And I claim that this is indeed a star coloring. So claim is a star coloring. And suppose not. Then by the definition of star coloring, there is a bicolored P4. P4. Right? Say V1, V2, V3, V4. And V1 and V3 have the same color. V2 and V4 have the same color. Okay. Now V1 and V3 have the same color, which means that they are located in the same level. V1, V3, and V2 is a common neighbor of V1 and V3, which means that V2 is the common ancestor of these two. So V2 is the common ancestor of V1 and V3. And similarly, V3 is the common ancestor of V and V4. V3 is the common ancestor of V2 and V4. So this is a contradiction because it means that the level of V2 is less than the level of V3, but it implies that the level of V3 is less than level of V2. Okay, so phi is a star coloring, and this coloring. So yeah, this coloring is n star coloring. Okay, so Pn satisfies the condition. Okay. And in addition, you can also show that you can easily show that every subdivided star satisfies the condition. Just exercise problem.
So you subdivide every edge exactly once?
No.
Or
Just whatever. Yeah.
subdivision of star?
Yeah. Subdivision of star. Yeah. Yes. Not only once. Okay. Then, in general, what can you say about this graph F? Okay, so these examples show that so P and N, a subdivision of star satisfy that condition, but in general, what can you say? And in our paper, we characterized all such graphs F. So this is theorem, our theorem. And itself this year let F be a graph, then F satisfies the condition in the question if and only if F is a forest. Okay, it's a little bit long, so F is forest in which now we are going to look at just large degree vertices. So, and we are going to check the distance between them. So, F is first in which every pair of vertices with degree n is 3, and in the same component has even distance. Okay, again, so we show that if F satisfies that condition, then F must be a forest, such that in each component, the distance between two vertices with degree n is 3 is even. Okay, it's a little bit complicated, but okay, so I'm gonna explain where this forest came from.
Was any direction known before?
If and only if condition.
Yeah, so that are both directions?
Yes.
Or
Yes, we showed both. We showed both directions. And of course, this direction is easy, a little bit easy. Then okay, and this direction not easy. Okay. Not really difficult, but not easy. And in this talk, I'm just gonna talk about this one. Okay, we are going to define some class of graph. Say G, M, N is the graph obtained from complete graph with M vertices obtained from Km by replacing every edge by n two-edge path. Okay, so G for 2 is a graph obtained from K4. Replacing each edge by two-edge path. Okay, this is G for 2. And just observe that GMN is bipartite. Right? So you can partition it into two sets. So the set of original vertices and the set of new vertices. Okay? And they are independent. They are new vertices and they form an independent set. And also the original vertices form an independent set. So this partition gives you a bipartite graph. And also say this is a A and B. And if you look at the vertices in B, every vertex in B has degree 2. Okay, every new vertex has only 2 neighbors. Yeah, something like this. Okay. Something. Okay, and every pair of vertices in A have n common neighbors. Okay, so if you take 2 vertices from the original vertices, then they have two common neighbors. Okay, so GMN has these 2 properties. And I'm going to show that the star-chromatic number of GMN say G n plus 1 is greater than or equal to n. Because G n plus 1 is bipartite, its chromatic number is 2, but its star-chromatic number can be arbitrarily large. Okay, and I'm going to show this. Greater than n. And suppose there exists, okay. Just consider n propagatory. Proper n calorie. And we have by partition of G n plus 1, so bipartition.
Maybe you want to have a G n plus 1 n plus 1?
I think that's right. Yeah, I think that's right. And okay, and here A is a set of original vertices, and B is the set of new vertices. And now, because phi is an n coloring, so there exist two vertices A1 and A2 in A with the same color.
Why?
Oh, wait. Let me check. Okay. Let's define A and B again. So A is the set of original vertices, and B the set of new vertices. Now the number of the size of A is equal to n plus 1 by the definition of G n plus 1, right?
No. N?
No, we start from K.
Km.
Okay.
So that's why.
Okay, all right.
I
Yeah.
suggested.
Yeah. Okay. Yes, the size of A is equal to n plus 1. So by the Peajono principle, there exists two vertices in A such that they have the same color. Okay, now they have A1 and A2 have n common neighbors. So by applying Peajono principle again, there exists B1 and B2 common neighbors A1 and A2 such that they have the same color. Then A1, A2, B1, B2 induce P4, bicolored P4. Actually, A1, A2, B1, B2 induce bicolored C4. That's very important. So A1, A2, B1, B2 induce bicolored C4. So for every proper n coloring, you can always find bicolored C4, which means the bicolored P4. So you cannot color. You cannot stack colors G n plus 1, n with n colors. Okay, so to show that this direction, so F satisfies that condition. So first observe that F is a forest. Okay, this is because so every F-free graph, the chromatic number of a graph is n most the star-chromatic number of the graph, right? So the first theorem, by the first theorem,
you should maybe say that the first theorem is also if and only if.
Yes, that's right. Yeah. Okay, great. Let me change the theorem. Now F here, F is a graph. Then there is, so then every F-free graph has bounded chromatic number if and only if F is a forest. Okay. Okay, thank you. Yeah. Then this theorem implies that F is a forest. And second, because of this graph, Gn plus 1 and F must be a subgraph of this one. So Gn plus 1 and for some n. Otherwise, you can take F-free graph Gn plus 1, n with very large star-chromatic number. And these two imply that F must be this one. This one. Okay, actually, so this direction is quite easy. So if you can find such a graph, then yeah, it implies that F is a forest. F is a sub-forest of this graph. Okay, and yeah, because this graph has this condition, so we can conclude this. Okay, so we are done with star-chromatic number. Well, how about acyclic coloring? Yeah. Okay. Yeah. I'm sorry. Yeah.
Can you give us some sort of idea of how the interaction goes?
Oh yeah. Yeah. Okay. Okay. Yeah. Okay, just consider, so for this F, consider F-free graph G. Okay, and we are going to partition VG into two sets. One set has small maximum degree, small degree. So every vertex here has small degree, say M. I don't remember exactly what M is. M is some function of the size of F. Okay, and this vertex has some large degree, so degree greater than M. And we can color each part independently. So because it has a small maximum degree, you can use, maybe I erased it. So you have, because the maximum degree is small, you need just M squared plus 1 color to color this part. And for this part, because every vertex has every vertex has large degree. So for this part, okay, say this part is A and this part is B. Is free, F free. This implies that is, say, F prime free, where F prime is a kind of subgraph, some subgraph F, not a subgraph, but F you can obtain F prime from F by some operation, but I'm not gonna, yeah. Yeah. So now you can use some induction. Okay. So if we assume that this is true for every for s smaller than f, then you can use induction here. Right? So you can color this part, and then when you combine A and B, maybe it generates some bicolored P4, like. So we are going to color each part independently, but when you combine them, maybe it generates like this. Okay, so we need one more some tool to manipulate this. So this part implies that you can color. There is a say m prime. There exists m prime star coloring of G of A, and so you can show that there exists some coloring, say used some phi coloring of such that if U and V have a common neighbor in B, then they have different colors. Okay, and then we are going to use these two colors to color this, the product of these two colors, right? Then this coloring doesn't generate this AB, bicolor P4. And that is just brief explanation of the proof. Okay. Yeah. And for acyclic coloring, okay, let me define acyclic coloring there. It's just a proper coloring with no bicolored cycles. Okay, so the union of two color. So this is just proper coloring such that the union of two colors induce forest. Okay, so this is a kind of a weaker coloring than star coloring. Okay. And we show that this theorem still works for acyclic coloring. So and the proof is exact same. So this is because it also has large acyclic coloring. Because for every n proper coloring, you can always find bicolored C4. So it always have so it has large acyclic coloring. And okay. So, star coloring is a proper coloring with no bicolored P4. No bicolored P4. And acyclic coloring is a proper coloring with no bicolored cycles. And two distant coloring is a proper coloring with no bicolored P2. P3. Okay. So they are just defined as some forbidden subgraph. They are defined by forbidden subgraph, right? So we extended this concept. We defined H avoiding coloring. This is just proper coloring with no bicolored H. Okay, so here H is a graph and H avoiding coloring is a proper coloring with no bicolored H. So P for avoiding coloring is star coloring, and P3 avoiding coloring is two distant coloring, so on. And we also developed such a theorem, our theorem, for H avoiding coloring for some graph H. So our main theorem characterizes forbidden all forbidden subgraphs for bounded H avoiding coloring for some H. Okay, I'm not going to specify what H is here. Okay, just we show that. So the first, I mean, there are different theorems. That is the corollary of our main theorem. Okay, so actually we show some stronger than that theorem, and indeed that is just corollary of our main theorem. And but I'm not gonna state this theorem exactly.
So sorry, I don't understand.
Yep.
So you're saying you have your forests where the
So,
large degree vertices are even distance from each other, and you're saying you've characterized all graphs H for which that's the correct answer?
okay, so this theorem is an answer for that question.
Right.
Okay, and here we defined avoiding coloring, which is a generalization of coloring, and we also show that. So yeah, we give an answer to that question for H avoiding coloring. For some
The answer same for different H, or is it different?
So for H is P4.
Yeah, almost
it's
the same.
that theorem, right?
I'm sorry.
When H is P4, it's this theorem,
Right.
right?
Uh,
And when H
yeah, yes, that's right. Yeah,
is a
yeah,
cycle,
yes,
it's that theorem.
yeah, yeah.
Okay, and what other?
And okay,
Tell us one.
okay. Let me say for which H. So, actually, this H just a forest obtained from. That's okay. Let me state. H is a forest. It is the same. Say this class H. So okay, this class H.
Oh, whenever H is such a graph,
Yes,
it has
yes.
the same characterization.
Almost same characterization. I mean,
It does not contain cycles, it is supposed. So basically coloring is.
Well, it doesn't cover basically coloring yet, but
yeah.
anyway.
Yeah. So if H, okay. So our main theorem characterize all for the subgraph for this for H, and if H is a star forest, it's not a star forest, then the results are the same. Do you understand?
Oh.
When the problem is when H is star forest, but in this case the problem becomes easier.
People is not a star forest.
Okay, here P4 and here A,
This is not a star forest, and the results are same.
Yes.
Same. So.
Okay, so if H is a member of this class and if H is not a forest, then the results are same. But if H is a star forest, then actually the problem becomes easier and you can characterize it very easily. Okay, and you have some problems. The first problem is we don't know forbidden subgraphs for bounded K33 chromatic number. So K33 is the smallest graph that we don't know the answer. And another problem is so it is also interesting to consider least version. For this theorem. Actually, at one time we thought that the proof worked for least coloring, but while writing we found a lot of gaps and we just gave up. And so we don't know about the least version. Okay, I'm done. And